I'm going to do a quick video on changing the limits using U substitution. And sounds fancy, I know, but really you've been hopefully doing some of this in your last class. Let's just find one solution to the equation, sine of 3x equals root 3 over 2. You probably let 3x equal probably some letter. I'm picking U just because that's the topic of the little video here is U substitution. So I'm substituting a simpler symbol for a more complicated term. And then we're going to solve with the simpler situation. So the sine of U equals root 3 over 2. So U is pi over 3. Then you come back to letting U become 3x, and 3x equals pi over 3, x equals pi over 9. 20-degree angle times 360-degree angle giving you root 3 over 2. Hopefully that's nothing new. Hopefully you had that practice in your last class. And if not, well, make the best of it. But you can certainly learn how to do these problems without having the knowledge of the trig over here. So a month from now, you probably won't even need U substitution to do these problems. Let's see, I got a little reflection there. Let's see if I can look around that. Where is that coming from? It's from the light above here. All right, so I'll try to rewrite this so that it's in a little better position. X squared plus 1 to the 5th dx. Let's see if that gets out of the glare there. Still there a little bit. We'll deal with it. So I'm going to get rid of this and bring it over here. Let's go. The integral x squared plus 1 to the 5th dx. All right. And we're going to do a definite integral, which means a specific area, and we'll go from 0 to 2. All right, and I'll do it without U substitution, and then we'll go back and change the limits and find out that it's a technique that simplifies the process. It's really just a shortcut. So a lot of times integrals are written this way, but it might be easier to see the chain rule. If you were to take this derivative, you would get a 2x at the end, right? Well, that is the derivative of this. And here we only have x. So sometimes it's nice to try to visualize the chain rule that this came from. And if you reverse the order of the two expressions, sometimes it's a little easier to see, but it's also a little more awkward in some situations where the arguments of a function seem to blend into the multiplication. So we'll leave it as this. And so x squared plus 1 to the 5th becomes x squared plus 1 to the 6th divided by 6. And there should be a 2 here. It isn't, so this is 1/2. We're going from 0 to 2. And now when we plug in the integers, 2 squared, 4 plus 1 is 5 to the 6 over 6. And we plug in a 0, we get minus 1 over 6. And that would be the answer to the area under this curve, all right, which we don't really have a good feeling for in terms of what it looks like, and not necessary at this point. We're just looking at pure mechanics. So eventually I substitute in 2 for the expression and do the math. So how can we make that process a little easier? Well, with U substitution, which many of you probably needed to get to here, you would have let U equal x squared plus 1, and du equals 2x dx, and du over 2x equals dx. Okay? And so that means that we're substituting x squared plus 1 now becomes the letter u, and dx becomes du over 2x. And maybe we can see the problem here is if you put a 2 in here, you don't get 5 to the 6th. You're going to get 2 to the 6th, and that's not the same thing. So we actually have to change these limits. And if we do so, we can come over here and we can go, oh, I use 0 to 2 with this expression. What do I need so that it's the same thing? Well, if I drop a 2 in, I need that 5. And if I drop a 0 in, I need that 1. All right, so let me highlight that by getting rid of this. Right? So once you change to the letter U, then you have to change these limits, these parameters. And so now they have become 1 to 5. And then you can do what? Cancel the x's, take the 1/2 out, and now we can do the integration. But the integration is no longer this, because this is changed to U, this is changed to 5, and this is changed to 1. And so now what do I get? Because that's certainly an easier integration than the one that preceded it. Well, when I drop a 5 in, I'm still going to get 1/2, 5 to the 6 over 6. And when I drop the 1 in, minus 1/6. Okay, so getting the same answer. So it's best to, when dealing with U substitution, to make immediate change right here. All right, now what type of problems am I going to ask you on tests and on worksheets to try to sort out? Because we're not going to then do the actual math at the end. We just want to be able to make this process a little easier. So let's say I gave you something like 1 to 2, 2x squared cosine x cubed dx. And what you'll see on my worksheets and on tests will be fill in the blanks. Okay, you're just going to fill in the blanks. All right, so what's our U? X cubed. All right, let's get our change in limits right away. So if I'm changing to U, that means I'm doing this. Okay, and if it's from 1 to 2, well, when I substitute, it really becomes 8. And it becomes 1. So 1 to 8. And du equals 3x squared dx. Therefore, du over 3x squared equals dx. So I have another substitution here, where dx becomes du over 3x squared. Hopefully you can see that 2/3 can come out. What happens to the x squareds? They cancel. And so final answer, 2/3, 1 to 8, cosine u, du, and you filled in the boxes. And let's try one more. And with a little practice, you don't even have to write the u's. Let's do 4x e to the 5x dx. You're pausing the video, I assume. Let's go from what to what? Let's go from 0 to 3. Okay, so what? Oops, I got a mistake here. I got to do 5x squared, and we'll make this. I'll make this 7x. All right. So I got to make sure that there's some kind of chain rule situation here. All right. So what's u going to be in this case? 5x squared. So we're going to change our limits immediately. They were 0 to 3. They now are 0 to 45. So this is okay. This changes to 45. This changes to u. Continuing on here, we got du over 10x equals dx. So I've got a new substitution for dx. It's du over 10x. I can see that 7/10 comes out. 0 to 45, e to the u, du is my new integration. And just finishing it off, we've got 7/10. What is the integral of e to the u? It is e to the u. And we're going to go from 0 to 45. And then we could do the rest of the fundamental theorem. And this process gets simplified a little bit. Just a little bit. Saves some time and energy. All right, so one last one. And then you'll be seeing them the rest of the way. And let's see. Let's do, let's just do one like we started with. Let's do 4x squared. Let's do 5x cubed minus 2 to the 7th dx. And let's go from 1 to 2. And let's see if you can fill in the boxes. All right, so I want to just, I guess I'll do it with you. So u is equal to 5x cubed minus 2, and we're going to go from 1 to 2. 1 to 2, if I drop a 2 in, 20 minus 2, I believe is 18. If I drop a 1 in, looks like it's 3. So this is going to be 3 to 18. I guess I didn't need this down here. All right, we now have, oh, I wrote the wrong thing here, 5x cubed. Excuse me. So I got to go back and do this again. From 1 to 2, 40 minus 2 is 38. And when I drop a 1 in, that's still 3. So now I've got 5x cubed minus 2, which is my u statement. My dx is going to be du over, what do we got here? 15x squared. Okay, so that means I can take 4/15 out, and the x squareds cancel. And that's my new problem. And that's what I'll want you to write down on your tests and homeworks and worksheets. All right, so that's that.